Hi, in this video we are going to discuss valence shell electron pair repulsion theory. A molecule is not flat chemistry, it is a 3D art painted by electrons. And once you master VSEPR theory concept, you will be able to look at a molecule to read a formula and mentally rotate a molecule in 3D, just because you understood how electrons behave in space. But before to start the VSEPR theory, we should need to take a step back and should learn about the Lewis structure. Once these basics are clear, VSEPR theory becomes simple, visual, and beautiful. This is the foundation of VSEPR theory. As the VSEPR theory is all about electron and Lewis structure is the 2D map of electrons. Lewis structure tells which electrons are shared between atoms, which are called bond pair electrons, and which electrons belong to only one atom, which are called lone pair electrons. For example, carbon has 4 valence electrons, as we can see through its electronic configuration. We can write its Lewis structure by 4 dots, and hydrogen has 1 electron. Carbon shares its valence electron with the electrons of 4 hydrogen atoms and forms CH4 molecule. This is the Lewis structure of CH4 molecule, which shows that there are 4 bond pair electrons and there is no lone pair electrons. Lewis structure of molecule should follow octet and duplet rules. As here CH4 carbon has 8 electrons and hydrogen has 2 electrons. And in case of nitrogen, it has 5 valence electrons as it belongs to fifth group. And we can represent its Lewis structure by 5 dots. Out of 5, 3 electrons are shared with the 3 electrons of 3 hydrogen atoms and form ammonia molecule which have this Lewis structure, which shows that there is 1 lone pair electron and 3 bond pair electrons. We can also represent ammonia molecule in this way, which also shows there is 1 lone pair electron and 3 bond pair electrons. And here nitrogen and hydrogen also follow duplet and octet rule. In case of unique compound like NaCl, here sodium has 1 electron and chlorine has 3 valence electron. Sodium donates its valence electron to chlorine and forms sodium chloride molecule, which has 3 lone pair electron and 1 bond pair electron. Lewis structure is all about valence electron and VSEPR is also all about valence electron. In 1940, Sedgwick and Paul developed this theory. According to VSEPR theory, valence electron which can be bond pair electron and as well as lone pair electron. These valence electrons arranged in such a way that there should be minimum repulsion or steric hindrance. And there should be maximum bond angles and maximum gap among bonds. This is the basic assumption of VSEPR theory. For example, aluminum trichloride. Here aluminum is the central atom which is bonded by 3 chlorine atoms. And we can represent this molecule in this way, but here at one place there is maximum gap or minimum repulsion. And at other place there is minimum gap or maximum repulsion. So this molecule arranged in this way. In this molecule, the central atom has no lone pair electron and 3 bond pair electrons. All the bonds are equally spaced and form 120 bond angle and trigonal geometry. And in case of ammonia, here the central atom nitrogen is also bonded with 3 atoms, but this has not trigonal geometry. This is because here the central atom has 1 lone pair electron. Here the lone pair electron causes repulsion and suppresses the bond pair electron or bond angle. And here the bond angle is 107 degree, which is due to lone pair electrons, and this forms trigonal pyramidal geometry. So, although in aluminum trichloride and in ammonia, the central atom are bonded with the same number of atoms but the geometry is not same. This is because the bond pair electron as well as the lone pair electron of the central atoms both affect the geometry of the molecules. Let us discuss some point of the VSEPR theory before to assign the geometry of molecule. The first one is the geometry of molecule is affected by both bond pair electron as well as lone pair electrons. For example, as we have discussed, ammonia and aluminum trichloride both have the same number of atoms but different geometry. This is because ammonia has lone pair electron as well as bond pair electrons, and aluminum trichloride has only bond pair electrons. So this is the reason ammonia has trigonal pyramidal geometry and aluminum trichloride has trigonal geometry. The second point of the VSEPR theory is space. The lone pair electrons have higher space as compared to bond pair electrons. For example, in stannic chloride molecule. Here, the Sn is the central atom which has one lone pair electron and two bond pair electrons. Here, the lone pair electrons are spread more, having the higher charge density or occupied more space. While on the other hand, the bond pair electrons are less separated and have less charge density. This is because the lone pair electrons are only attracted by one atom which is Sn, and the bond pair electrons are attracted by both nuclei of Sn atom and chlorine atom. So these are less occupied as compared to lone pair electrons. The third point is the repulsion. The lone pair electrons have greater repulsion as compared to bond pair electrons. This is just because the lone pair electrons have higher charge density. For example, in CH4 molecule, all the bonds are equally spaced because there is no lone pair electron and there are 4 bond pair electrons. And in case of ammonia molecule, the central atom nitrogen has one lone pair electron which causes repulsion or suppress the bond pair electrons. And in case of water molecule, the central atom oxygen has two lone pair electrons which cause much repulsion and suppress the bond pair electrons strongly. So we can say as the number of lone pair electrons increase, the repulsion on bond pair electrons increase. And we can assign the magnitude of repulsion as lone pair electron have greater repulsion as compared to lone pair electron bond pair electrons, which have greater repulsion as compared to bond pair electrons bond pair electrons. The fourth point is the angle. As the repulsion increases, the bond angle decreases. As we have discussed in the above example, the repulsion increases from CH4 to ammonia and water molecule, and bond angle decreases in this order. For example, in CH4 molecule, the bond angle is 109.5. In NH3 molecule, the central atom has one lone pair electron which causes repulsion, so repulsion increase and bond angle decrease from 109 to 107. And in case of water molecule, there are two lone pair electrons which cause greater repulsion and bond angle decrease to 104. So as the repulsion increase, bond angle decrease. The fifth point is the multiple bonds which don't affect the geometry of molecules. Like single, double and triple bond have the same geometry when there are same number of atoms in molecules. And the central atom has same number of lone pair electrons plus bond pair electrons. In these conditions, the geometry of molecule will be same. For example, beryllium chloride molecule which have single bonds, carbon dioxide which have double bonds, and hydrogen cyanide which have triple bond. All these molecules having single, double and triple bond having the linear geometry. But the charge density of multiple bond is greater as compared to single bonds. The fifth point is the electronegativity. As the electronegativity of B atom increase, the repulsion of bond pair electron decrease, and the repulsion of lone pair electrons on the bond pair electron increase. For example, in phosphorus triiodide molecule, in phosphorus tribromide molecule, and in phosphorus trichloride molecule. The electronegativity of B atom is increasing from phosphorus iodide to phosphorus chloride molecule. As the electronegativity of chlorine atom is greater than bromine and the electronegativity of bromine is greater than iodine. So as the electronegativity of B atom increase, the tendency to attack the bond pair electron increase and the bond pair electron move away from the lone pair electrons. In this way, the influence of lone pair electron on bond pair electron increase and bond angle decrease from 102 to 101.5 to 100 degree. And the sixth point of the VSEPR theory is distortion in geometry. According to this point, the lone pair electrons in molecule cause distortion in geometry, which is well explained by the Gillespie. Gillespie modified the VSEPR theory and gave some rule to assign the geometry of molecules. Among the rules of Gillespie, the first one is the regular shape. The shape of the molecule will be regular when the central atom has only bond pair electrons. For example, in CH4 molecule, the central atom is carbon which has no lone pair electrons and has 4 bond pair electrons. So according to this rule, the geometry of this molecule is regular. In this molecule, the central atom has 4 bond pair electrons, and the geometry will be linear when the central atom has 2 bond pair electrons. Trigonal geometry when the central atom has 3 bond pair electrons. Tetrahedral geometry when the central atom has 4 bond pair electrons. Trigonal bipyramidal geometry when the central atom has 5 bond pair electrons. And octahedral geometry when the central atom has 6 bond pair electrons. These are all regular shape when the central atom has only bond pair electrons, no lone pair electrons. The second rule of Gillespie is the shape of molecule will be irregular when the central atom have lone pair electron plus bond pair electrons. For example, in ammonia molecule, the central atom nitrogen have 1 lone pair electron and 3 bond pair electron. So the geometry of this molecule will be irregular. And the geometry of this molecule is trigonal pyramid, which is not regular shape as we have mentioned above. So the shapes of the molecule turn from regular to irregular when the central atom has lone pair electron. The third rule is the electronegativity of B atom. As the electronegativity of B atom increase, the bond angle decrease. For example, as we have discussed in the phosphorus triiodide molecule, the phosphorus tribromide molecule, and in phosphorus trichloride molecule, the electronegativity of B atom is increasing. So as the electronegativity of B atom is increasing, the bond angle is going to decrease. This is because the influence of bond pair electron decrease and the influence of lone pair electron increase as the electronegativity of B atom increase. As the electronegative atom attract the bond pair electron and lone pair electron find the space to repel the bonds. The fourth rule of Gillespie is multiple bond. Multiple bonds don't affect the geometry of molecules. For example, single, double, and triple bond have the same geometry in molecules like beryllium chloride, carbon dioxide, and hydrogen cyanide, which have single, double, and triple bond, but the geometry of all these molecules is linear. But as the multiple bond having the greater charge density have more repulsion. For example, in SOF4 molecule, the central atom is the sulfur which has one double bond and four single bond. Here the repulsion between single and double bond is greater as compared to repulsion between single bonds. This is just because the double bond having the greater charge density as compared to single bonds. And the fifth rule of Gillespie is when the central atom have greater number of electron or filled shell causes more repulsion as compared to those which have incomplete shell or less number of electrons. For example, in hydrogen sulfide and water molecule, the sulfur have greater number of electrons. So this causes more repulsion as compared to oxygen atom in water molecule, as oxygen has less number of electron. This is the reason in hydrogen sulfide the bond angle is 92 degree and in water molecule the bond angle is 104 degree. So we can summarize that as the number of electron or the charge density increase, the repulsion increase and the bond angle decrease. In this video we will apply some basic assumptions, point and the rules of the VSEPR theory to assign the geometry of molecules. ABE. This is the general formula of VSEPR model. Here A is the central atom, B is the bonded atom with central atom, and E is the number of lone pair electron on the central atom. Let us start from the first system of VSEPR model, which is AB2 system. In this system, A is the central atom which is bonded with two other atoms, and in this system the central atom having 0 lone pair electrons. For example, we say that the compound of group 2 elements form this system, like beryllium chloride, beryllium bromide, cadmium chloride, etc. In all these compounds, the central atom is bonded with two other atoms and having 0 lone pair electrons. This is the geometry of beryllium chloride, carbon dioxide, neutronium ion, and hydrogen cyanide. The geometry of all these compounds is linear, and these all compounds belong to AB2 system. As we have discussed that multiple bonds do not affect the geometry of molecule, these compounds having single, double, and triple bond have the linear geometry and having bond angle 180 degree. And in this system, all the central atom are sp hybridoids having maximum bond angle and minimum repulsion. AB3 system. Here is the central atom which is bonded with three other atoms and having 0 lone pair electrons. For example, we say that the compound of the group 3 elements like boron trichloride, boron trifluoride, aluminum trichloride, etc. or belong to AB3 system. This is the geometry of aluminum trichloride. Here aluminum is the central atom which is bonded with other three atoms having 0 lone pair electrons. Here the bond angles are 120 degree and the geometry of this molecule is trigonal. This is flat or planar molecule. Carbonate ion. This also belongs to AB theory system, but here the bond angle is not exactly 120 degree. As in COCl2 molecule. Here the double bond do not affect the geometry, but having the greater charge density cause greater repulsion. So due to greater repulsion, the bond angle reduced from 120 to 111.4 degree. And here bond angle increased from 120 to 124.3 degree. But the geometry of all these molecules are trigonal and all the central atoms are sp2 hybridize. AB2E system. This is the subsystem of AB theory system. Here the A is the central atom which is bonded with two other atoms and having one lone pair electron. For example, sulfur dioxide SnCl2 molecule or belong to AB2E system. This is the geometry of sulfur dioxide and SnCl2 molecule. Here the central atom having one lone pair electron and bonded with two other atoms. So these belong to AB2E system. And as the lone pair electron cause greater repulsion as compared to bond pair electrons, so the bond angle decrease and the bond angle is less than 120 degree. The electronic geometry of these molecules are trigonal, but the geometry of molecules are weird band shape. And the central atom in this system is also sp2 hybridize. AB4 system. Here is the central atom which is bonded with four other atoms and having zero lone pair electrons. For example, compound of group 4 elements like CH4, CCl4, SiF4, etc. All these molecules belong to AB4 system. This is CH4 molecule. This is not planar molecule. The bond angles are 109.5 degree and the geometry of this molecule is tetrahedral. And here the central atom is sp3 hybridize. Ammonium ion, which have one coordinate covalent bond, sulfate ion, and ClO4 anion. These compounds are also belong to AB4 system having tetrahedral geometry and the central atoms are sp3 hybridize. AB3E system. This is the subsystem of AB4 system. Here is the central atom which is bonded with three other atoms and having one lone pair electron. For example, NH3PI3 molecules belong to AB3E system. This is the geometry of NH3 molecule, which have one lone pair electron and three bonded atoms. Here, the lone pair electrons cause greater repulsion, so the bond angle decreases from 109 to 107 degree. And the electronic geometry is tetrahedral, but the geometry of this molecule is trigonal pyramid. In this subsystem, the central atom is also sp3 hybridized. AB2E2 system. This is also subsystem of AB4 system. Here is the central atom which is bonded with two other atoms and having two lone pair electrons. For example, water, hydrogen sulfide Cl2O molecules or belong to this system. This is the geometry of water molecule. Here, the central atom oxygen has two lone pair electrons and two bonded atoms. These two lone pair electrons cause greater repulsion, so the bond angle decreases from 109 to 104 degree. And the bond angle in hydrogen sulfide is 92 degree, which is due to greater size of sulfur or greater repulsion. The electronic geometry of these molecules are tetrahedral, but the geometry of these molecules are V-shaped, and here the central atom is also sp3 hybridized. AB5 system. Here is the central atom which is bonded with 5 other atoms and having 0 lone pair electrons. For example, compounds of group 5 elements like PCl5, AsCl5, PF5, etc. belong to AB5 system. This is the geometry of PCl5 molecule. Here phosphorus is central atom which is bonded with 5 other atoms having 0 lone pair electrons. And the geometry of this molecule is trigonal bipyramid, as this forms trigonal shape and two pyramids. So the geometry of all the molecules belong to AB5 system is trigonal bipyramid. In this molecule, there are two types of bond. One is axial bond and other is equatorial bond. The two bonds which are above and below the plane are axial bonds, and the three bonds which are on plane, these are equatorial bonds. And the bond angle between axial equatorial bond is 90 degree. Bond angle between equatorial bond is 120 degree. And the bond angle between axial bond is 180 degree. So there are three kinds of bond angles. Axial equatorial bond angle, which is 90 degree. Equatorial bond angle, which is 120 degree. And axial bond angle, which is 180 degree. Axial bonds are weaker as compared to equatorial bonds. In chemical reaction, by heating PCl5, first axial Cl removed because of larger bond length and weaker bond strength. This is because axial have less space to occupy or less bond angle, and more steric is there, so these are less stable. After removing axial chlorine, this form AB2E system. And in AB5 system, all the central atoms are sp3 dehybridized. AB4E system. This is the subsystem of AB5 system. Here is the central atom which is bonded with 4 other atoms and having 1 lone pair electron. For example, SF4, TeCl4, SCl4 or belong to this system. This is the geometry of SCl4 molecule. Here, 1 lone pair electron cause repulsion, so the bond angle become less than 90 and less than 180 degree between axial equatorial bond and axial bond. The electronic geometry is trigonal bipyramid, and the geometry of this molecule is seesaw, and the central atom is also again sp3 dehybridized. AB3E2 system. This is the subsystem of AB5 system. Here A is the central atom which is bonded with 3 other atoms and having 2 lone pair electrons. For example, ClF3 molecule belong to this group. This is the geometry of ClF3 molecule. Here, the central atom has 2 lone pair electrons which cause greater repulsion, so the bond angle become more less than 90 degree between axial equatorial bond and more less than 180 degree between axial bond. So we can summarize as the number of lone pair electron increase, the repulsion increase, and the bond angle decrease. The electronic geometry of this molecule is trigonal bipyramid, and the geometry of this molecule is T-shape. And the central atom is again sp3 dehybridized. AB2E3 system. This is also subsystem of AB5 system. Here is central atom which is bonded with two other atoms and having three lone pair electrons. For example, XeF2 molecule belong to this system. This is the geometry of XeF2 molecule. Here the central atom have two bonded atom and three lone pair electrons. One lone pair electron on one side and two lone pair electron on other side cause repulsion and form the geometry of this molecule linear. Although the electronic geometry is trigonal bipyramid and the central atom is sp3 dehybridized. AB6 system. Here is central atom which is bonded with other 6 atoms and having 0 lone pair electrons. For example, compound of group 6 element like SF6 molecule belong to this system. This is the geometry of SF6 molecule. And the geometry of this system or this molecule has 8 heads. 4 heads on one side and 4 heads on other side. So we say that the geometry of this molecule is octahedral, having 8 heads. In this system or molecule, there are also two types of bond angles, which are 90 degree and 180 degree. And the central atom may have sp3d2 or d2sp3 hybridization. AB5E system. This is the subsystem of AB6 system. Here is the central atom which is bonded with 5 other atoms and having one lone pair electron. For example, Br, F5, IF5 molecules belong to this system. This is IF5 molecule. Here the central atom iodine is bonded with 5 other atoms and having one lone pair electron. The electronic geometry of this molecule is octahedral, and the geometry of this molecule is square pyramid. As this forms square shape or pyramid shape, so we say that the geometry of this molecule or this system is square pyramid. Here one lone pair electron cause repulsion, so the bond angle becomes less than 90 degree. And the central atom has sp3d2 hybridization. AB4E2 system. This is also the subsystem of AB6 system. Here is the central atom which is bonded with 4 other atoms and having 2 lone pair electrons. For example, XeF4 molecule belong to this system. This is XeF4 molecule. Here the central atom is bonded with 4 other atoms and having 2 lone pair electrons. And the geometry of this molecule is square planar geometry. Although the electronic geometry of this molecule is octahedral. Here, this system or this molecule have 2 lone pair electrons which cause greater repulsion and the angle becomes more less than 90 degree. We can verify this system as Xe belong to 8 group, having 8 valence electrons, 4 involved in bonding and 4 valence electron form 2 lone pair electrons. So this is AB4E2 system. And in this system the central atom is also again sp3d2 hybridized. So we also summarize in this system as the number of lone pair electron increase and the number of bond per electron decrease, repulsion increase, and the bond angle decrease. These are AB6, AB5E, and AB4E2 systems, which represent as the number of lone per electron increase, the bond angle decrease. AB7 system. Here is central atom which is bonded with 7 other atoms and having 0 lone pair electrons. For example, compounds or molecule of the group 7 elements like IF7 form this system. This is IF7 molecule. Here iodine is the central atom which is bonded with 7 other atoms and have 0 lone pair electrons. And the geometry of this system or this molecule is pentagonal bipyramid. As this molecule form pentagonal shape and 2 pyramids. One pyramids on one side and other pyramids on other side. So the geometry of this molecule or this system is called pentagonal bipyramid. This system also have 3 types of bond angle as AB5 system. The bond angle between equatorial bond is 72 degree. The bond angle between axial bond is 180 degree and the bond angle between equatorial axial bond is 90 degree. So we can say this system has 3 types of bond angle. Axial equatorial which is 90 degree, axial which is 180 degree and equatorial which is 72 degree. In this system, the central atom has sp3d3 hybridization and the geometry is pentagonal bipyramid. Thanks for watching and please comment if you have any question.